Hey everyone, this is the video for 5.1, combining functions. And so right now we're about to start talking about exponential and logarithmic functions. So in the realm of like family reunions, we've had linear family reunion, quadratic family reunion. We've been privy to a little bit of the cubic family reunion, quartic, quintic. We've even gotten into some square roots and absolute value functions. But now we're about to introduce two new families which are actually the complete opposites of each other. So we're looking at the exponential function and the logarithmic function. These two families are inverses of one another. So one undoes the other. But we'll get into that all a little bit later. Let's take a slow dive into it. And let's get started right now. With operations on functions, we have basically a car that is clearly traveling along a path. Okay, so the dashed line is where the car was and the blue car is where it is now. And so R of X is the reaction distance. So let's say this car was driving and it saw something in the road. Then it would take this amount of space to actually react. And then they have B of X, which represents the braking distance. Once they apply the brake here, then it takes that long for it to stop. So this is a function of a car that's moving that has to encounter a reaction distance and reaction distance and a braking distance. So assume a driver has a reaction time of 1.5 seconds. We compute two functions to model the total stopping distance of the car. First, we have to look at the reaction distance. And that reaction distance is given by 11 over 5x. So that's the amount of like time and the speed, I guess. So the distance, braking distance is given in feet of 1 over 11x squared. First off, they gave us these functions and all we have to do is interpret them. So R of 55 and interpret the results. That means substitute 55 into the equation. So we put in 55 and we have 11 over 5 times 55, and that's 121 feet. So how long would it be? I mean, how many feet would the car still travel before the reaction is to put on your brake? 121 feet. So if a car was traveling at 55 miles per hour, that's what X represents, the speed, it would take them 121 feet of time in the time to react. Okay. If we evaluate B of 55, this is again a car traveling at 55 miles per hour. Well, now they know, oh, wait, I got to put on my brake. How many feet will it be before they actually stop? 275 feet. So a car traveling at 55 miles per hour will need 275 feet to stop once the driver begins to brake. So let's say a car driving 55 miles per hour sees something in the road. It would take them a total of 396 feet to stop, because first they got to take 121 to realize that they need to stop and apply the brake. As soon as they apply the brake, then there's still another 275 feet that they have to travel before the car comes to a complete stop. So basically that's how we got our addition together of the total time. Okay. So the way we interpret that is the total stopping distance of a car traveling 55 miles per hour, including time to react and brake, is 396 feet. Operations on functions. We can also model the stopping distance of a car graphically, where R of X is the reaction distance in feet and B of X is the braking distance. So again, we're still talking about the same stuff. So use the graph to evaluate R plus B of 40. Remember, this is the reaction speed and the braking speed at 40 miles per hour. So looking at 40 miles per hour, the reaction distance is 88 feet. The braking distance is 143 feet. 45 feet, sorry. And when you add those together, you get your 233 feet. So S represents the total stopping distance needed when we have the reaction and the break distance. Okay, this is a new example. Example 3. We can also study the numerical representation of the stopping distance, where R of X is the reaction distance and B of X is the breaking distance. So still the same kind of concept. We're going to just be using a table now to evaluate the reaction and the break distance together. So at 22 miles per hour, you need 48.4 feet to react and 44 feet to stop. So the total is 92.4 feet for S of X. So I think this example should make sense in terms of your car. You see something, your brain has to register first, then your brain registers, you have to apply the brake physically, and then boom, you finally stop. And so these represent those two different distances, and if we want to find total, we just add them together. So these are called operations on functions. When you have one function and another function, and you got to add them together, multiply them together, subtract them. For whatever reason, the application problem may ask you to do one of these different operations. So f of X and g of X are two different functions. You can add them together, you can subtract them, you can multiply them, or you can divide them. Of course, if we're dividing functions, we know that the denominator can never be 0. That's a rule that we've been dealing with all semester long. So that doesn't go anywhere, that's still here. Okay. The domain of each resulting function includes X values from both of the domains. So like if they say, what's the domain of the sum of this? Then if there was a restriction in F and a restriction in G, then that means there's a restriction in F plus G. So like whatever the domain is for both of them, you still have to consider both domains when you consider the entire domain. F of X and G of X use F of X and G of X to evaluate the expression symbolically. So we've looked at this from a verbal description. We've looked at this from a graph. We've looked at this from a table. The next thing is to look at this actually like in handwriting, okay? So F of G and F of X is this first function, X squared plus 1. G of X is this second function, X square root of X minus 1. And it says, can you add these two functions together? Evaluated at 5. So you're going to substitute 5 into both equations, get your number, and add those two numbers together. So if we put 5 in the first equation, we get 5 squared plus 1 is 25. 25 plus 1 is 26. And then the square root of 5, that's not a whole number. So subtracting that is going to be a decimal approximation. So we really just can leave it. Okay. So that's 26 plus the square root of 5 minus 1. Well, that 26 and that 1 are like terms. So you can do 26 minus 1 and get 25. So 25 plus the square root of 5 is the answer. This is still, you could go further. You could go further and actually estimate the square root of 5, but we don't want to do that. We want to leave it in exact terms. Okay. Looking at B, we're taking both functions and subtracting them, evaluated at 1. So write it down first. That's f of 1 minus g of 1. Substitute 1 into both equations and solve. 1 squared plus 1 is 2. And then square root of 1 is 1. Minus 1 makes 0. So we end up with 2 minus 0. The difference between A and B is the square root of 5. That's not a whole number. That's not a perfect square. Whereas square root of 1 is a perfect square, and it is 1. So square root of 1 minus 1, 1 minus 1 is 0. So the answer will be 2. For C, we have F times G. FG mean multiplication. So F times G of 0. So we're going to plug in F of 0 and then multiply by G of 0. Got to know what that means first. So let's substitute 0 in for both equations. In the first one, we get 0 squared plus 1 is 1. And square root of 0 minus 1. So square root of 0 again, that's perfect square, that's 0. minus 1 is -1. So we get +1 times -1. The negative is superior, so it ends up with -1 as our result. The last one, D, is f of 3 divided by g of 3. So we plug in 3 for each equation, and we continue. So that's 9 plus 1 is 10. Square root of 3 is not a perfect square, so we leave it. -1. I'm sorry. And so because that's not a perfect square, we can just leave it. And the 10 cannot be divided by either one of those because that's just not how you work with fractions. That is our denominator. And we leave it just like that. Don't do too much more. Okay. Use f of x and g of x to find the formula for each expression identified as domain. So this time we are going to identify the expression together, and then we're going to define the domain. So looking at the first one, we have a square root of x. We know that when you're taking the square root of a number, that means that our domain is all positive or non-negative numbers, 0 and up. So that is going to be our domain for f of x and g of x. Okay, it's going to have to be, we can only substitute in non-negative numbers. So f minus g of x is the same thing as f of x minus g of x. So we take these functions and we subtract them. We'll notice that when you subtract an entire function, you have to distribute that negative. So minus square root of x and minus 5 become minus square root of x plus 5, because a minus a negative makes a positive on that 5. So we got the square root of x plus 1 minus the square root of x plus 5. We're going to combine like terms here. Square root of x minus square root of x makes 0 x's. And 1 plus 5 makes 6. So my answer, my resultant is 6. The square root of x canceled out because you had one and you took one away. So now my domain, it doesn't have to be non-negative numbers. I'm sorry, I lied. The domain still stays the same because you have to consider the original function when you define the domain. So our domain is from 0 to infinity. Okay. That's the same thing for B, same function. So we definitely are still going to be dealing with non-negative numbers. And this time we know there's an additional piece where the denominator cannot be 0. So that is our function. We just put f of x over g of x. But for the domain, we have, from 0 to infinity. But since we're dividing by a function, we just know that that bottom function can never be equal to 0. So therefore, we have to actually set it equal to 0 and solve. Okay. What number would make this denominator 0? The answer is 25. Because the square root of 25 is 5. So 5 minus 5 is 0. So that's why we can't have x equals 25. Now, another way for us to see that is to do what we always do. Take the square root of x minus 5, so the bottom, and say it cannot equal 0, and work backwards. This question is what square root is equal to 5? We know that's 25. But you square both sides when you want to get rid of a square root, and you get x equals 25. So x cannot equal 25. So our domain is all the numbers 0 to positive infinity except 25. So we're going to have to write that in that way so we can exclude 25. 0 to 25 and 25 to infinity. All right, use f of x and g of x to find a formula for each expression identified as domain. Same exact thing, okay? Well, in this first one, when we look at the domain here, x can never be 0 because x is the denominator. So that's one of our restrictions. Uh-oh. G of X equals X squared. Well, that's all real numbers. So when we put these together for the domain, we're basically saying that the domain is all real numbers except 0, because you got to consider both of them. So f of X plus G of X is our first one. That's 1/2 plus X squared. Well, you can't really add fractions unless they have common denominators. So we have to make a common denominator. So we're going to end up with 1/X plus X squared over X. X cubed over X. Because we multiply the top and the bottom by X so that we can get an X in the denominator. When we do that, we get 1 plus X cubed equals over X. We have to basically find the common denominator. That's horrible. Let's see if I can write it with my screen down. Much better. In order to add fractions, you have to have a common denominator. So that's key. Okay. For the domain, we know that f of X is all real numbers except X equals 0. And for G of X, it's all real numbers. So we are going to put those together, all real numbers except for 0. So from negative infinity to 0, from 0 to positive infinity. Because we're multiplying these guys, this one's probably the most simplified. We still take the same domain and we just multiply. When you multiply a fraction, you just multiply straight across. So that's 1 times X squared and X times 1. So X squared over X. When you do that, they have something in common. So X squared is X over X. X times X over X. So then when you simplify, you just end up with just X. That's how we get with just X. The domain is the exact same as part A, because we just put the domains together. We don't have to make any extra considerations for the denominator because we weren't dividing. Use the graph to evaluate the expression if possible. So F plus G of X. So now we're just doing the same thing we've been doing, but we're looking at it from a graph. Okay. So F plus G of X. Lord, I can't get it out. Hold on, y'all. F plus G of 4. So F of X at 4, G of X of 4, and then add those two values together. So at 4, where's F of X? Is 9. At 4, where's G of X? Is 2. So we're going to do 9 plus 2 and make 11. So let's do that and show you what that look like. That's 9. That's 2. So when we add them together, we get 11. Okay. All right, so B, F minus G of 2, a negative 2. So let's find F of negative 2 and G of negative 2. So let's label a point on the graph. F of negative 2 is down there at negative 3. G of negative 2, G don't even go backwards to negative 2. Like there's no red spot at negative 2, red line or red function. So it doesn't exist. It's undefined. Therefore, you can't subtract nothing that don't exist. The answer is undefined. A lot of people would have put the answer was negative 3. But it's not negative 3. It's negative 3 minus undefined. That value is not defined. Therefore, the whole thing does not exist. F of 1 times G of 1. So F of 1 is 3. G of 1 is 1. 3 times 1 is 3. F of G of 0. F divided by G of 0. So we're going to do F of 0 and G of 0 and divide them. So F of 0 is 1. G of 0 is 0. So when we put this together, we got 1 divided by 0. Whoa, you can never divide by 0. What does that mean? That means that this is undefined. You can't divide by 0. From a table, same exact thing as from the graph, but this time we don't have to interpret the lines on the graph. We have the values right in front of us. So f plus g of -1. Okay. When x is -1, f is 4 and g is 2. So you add those two together and you get 6. When x is 2, f is 3 and g is 1. F times g of 2 makes 3 times 1. Oh, my bad. I start doing C. Let's do B. G minus f of 0. So we got g of x minus f of x. And we're looking at the 0 on the table when x is 0. So we're going to have g of 0 is 0. F of 0 is 1. 0 minus 1 is -1. The order matters. Y'all know the order matters. 2 minus 4 is not the same thing as 4 minus 2. So when you subtract, you got to make sure you put these numbers in order that they gave you. If they ask for f minus g, that's not the same thing as g minus f. Okay. C, f of g of 2. So let's find f of g and g, and I'm sorry, f of 2 and g of 2. F of 2 is 3, g of 2 is 1. Multiply them together and get 3. G divided by f of 0. So g of 0 is 0. F of 0 is 1. So 0 divided by 1 is 0. 0 divided by anything is 0. Now, if you try to divide by 0, you're undefined. Okay. All right, quick review, putting it all together before we move forward. Let g of x equal 3x squared minus 3x plus 2. Just can you evaluate the expression? I'm going to go fast through this because we already know that you know how to substitute values in and multiply and add and subtract. But you can do this on a calculator as well. Remember that g of 2 just means plug in 2 and evaluate. So 2 squared would be 4. 4 times 3 is 12. 12 minus 6 times 2, which is also 12. 12 minus 12 is 0, plus 2 makes 2. So again, I'm going to speed through all this. You can talk about it in class if you don't understand. But you just substituting values in and applying. So you can pause and try to do these on your own and then come back and check your work and see if it matches. Okay. Composition functions. Now, we've been adding, subtracting, multiplying, dividing functions. Now, composition functions mean you about to put a function inside of another function. Okay. So we're going to start off with an example first, and then we'll go into the symbolic and the graphical and the tabular. A function g of m approximates the number of gallons of gas needed for a vehicle to travel m miles. So g of m tells you the number of gallons of gas that you need to travel a certain number of miles. The function c of g gives you the cost of the gas for each gallon, or the number of gallons you have. So you got two different functions. One of them is you putting in miles and it'll tell you how many gallons you need. The other one, you put in the number of gallons you need, and it'll determine the cost, the total cost of that. We're gonna say that this is not real life because 4 gallons being $11 would be amazing. Anywho, use the tables to determine the average cost of traveling 300 miles. So you're starting off with 300 miles. This table tells you that you need 12 gallons of gas to do that. Then you go with this table and you say, hey, taking that 12, how much was it cost? $33.60. So notice that we start with the number of miles. Okay. And we put that in for the G, and we get out the number of gallons. Then we take the number of gallons and put that into C to determine the cost. Okay, so you start with input of one, which gives you a certain output. That output is now the input of the other one, which gives you the output that you wanted, which was cost in this case. So mathematical computation, we call it a composite function, composition function. You putting functions inside of other functions. The notation looks like this. It is confusing. Please do not let this confuse you. Let's break it down. C circle G. That circle means to put G inside of C, the number of gallons to find the cost. And the way you think about this is we start off with miles, we find gallons. We take gallons to find cost. And that's how I kind of go in backwards order. You start off with miles, miles gives you gallons, take gallons, gallons gives you cost. So you go in kind of this backwards fashion from the inside out. Okay. All right, so let's look at another example. The function C of F gives the average number of calories burned for walking F floors. So C of F tells you, you put in how many floors of stairs you're gonna walk. And then that gives you the number of calories that you burn. The function F of T gives you the number of floors an average person can walk in T minutes. F of T, you take minutes, and that'll give you the number of floors. So from what we have, these two functions have in common is floors. So basically we could take minutes, work backwards to get the number of floors, and then use that number of floors and then find the number of calories. So working inside out, I would say that we start with minutes. And that is actually called T for time. We start with the number of time. That'll give us the number of floors a person can run. Then we take them floors, and then that will give us the number of total calories burned. So that's what a composite function would look like, working inside out. F is what they have in common. So when I'm reading it again, I'm gonna slow this down because it's brand new. So when I'm reading this, I'm gonna say the function C of F gives number of calories for walking floors. F of T gives a number of floors. See, I see what's in common, floors and floors, that a person can walk in minutes. So we're working with minutes, floors, and calories. And you just got to realize how they're connected to each other. So what composition would be needed to determine 30 minutes? You start with time. You plug that into your floors function to find the number of floors. You take the number of floors and you plug that into your C of F function to find the number of calories burned. So there we go. C of F of 30. How we write that with a composite symbol. That symbol is just like add, subtract, multiply, divide. We just added a new symbol and it's an open circle and it just means to plug this function inside. So C of F of 30. This basically tells you to find F of 30 first. And then plug that F value into C. Okay. So this is just, again, by definition, how it looks and what it means. No important notes about the domains. So the domain of a composite function, X is all the valid inputs for G. So that's the domain for G. And then you get G of X, which is the valid domains for F. Okay. So let's do this together. Complete the following. So we need to find F of G of 2 and then G of F of 2. First off, the difference is we plug it in 2 into G first and then G into F. Versus over here, we plug it in 2 into F first and then f into g. Okay, so let's do it. The easiest way to learn it is to do it. So 2 into G, then G into F is what we're doing. So we're going to plug in 2 into G. So if we plug in 2 into G, it's 1/2. So then that's what G of 2 is. So then we take this 1/2 and plug that into F of X. So we got 1/2 squared plus 3 times 1/2 plus 2. And I'm going to slow this down. 1/2 squared is 1/4 plus 3 over 2 plus 2. Find the common denominator, that's 1/4 plus 6 over 4 plus 8 over 4. I just made all these have common denominator of 4. 8 plus 6 is 14 plus 1 is 15. That's how we get 15 over 4. You could also just use your calculator and solve it that way. On this next one, on the other hand, we're going to find G of F of 2. So we're going to plug the 2 into F first. Okay. By doing that, we have 2 squared plus 3 times 2 plus 2. So that's 4 plus 6 plus 2 is 12. Now we plug in 12 into G, and that's 1 over 12. Because G is 1 over X. Any questions? Pause the video, write your question down so that when we in class, you can ask your question. Notice that the results are not equal because the order matters. Okay. Next, we have find the composite functions defined by f of g of x and g of x. Same exact thing. See if they're equivalent. But we're gonna not do this with the value. We're gonna do this using symbols. We already know the answer, they're not equivalent. But let's keep working with it. The first one says take g of x and plug it into f of x. So g of x is 1 over x. So we're going to put 1 over x where x is in the function of f. 1 over x squared plus 3 times 1 over x plus 2. And that's what we end up with. Whereas over here, we're going to take f of x and plug it into g. So f of x is x squared plus 3x plus 2. We're going to plug that into g. So all of that is under 1. 1 over all of that. Is this the same as this? No, these are not the same. So therefore, the order does really matter. We're going to look at this one more way, symbolically, but we're going to talk about the domain. Okay. So we have our values of what they're equivalent to. We just found that on the other screen. Here, you can plug anything in for x except for 0, because you can never divide by 0. Okay, so anything except for 0. Same thing here. Well, if I plug in 0 here, I still get 2. So that kind of it's not really the same. So there's no restrictions for the domain on this first one. So we just say it can't be 0. Over here, we can say, okay, well, we're looking for 2 numbers that multiply to equal 2, but add to equal 3. That's 2 and 1. So in our denominator, we end up with x plus 2 and x plus 1. So x can never be -2, x can never be -1. Because if you do, you'll have -2 plus 2 makes 0. And then anything times 0 is still 0. It can't be -1 because we have 0. And anything times 0 again is still 0. So x cannot be -2 or -1. So X cannot be -2. X cannot be -1. So you see they have different domains. Okay, now using a graph, can we evaluate the composition? So f of g of 4. So the first thing we're gonna do is find f of 4, g of 4, and then plug it into f. So you're not doing the same line anymore. You kind of working your way around the graph. So what is g of 4? G of 4 is 2. Okay. Then we say plug 2 into f. So we go on 2 and we say, where is f? It's at 5. Okay. So remember that the output of one is the input of the other. So we started with 4. We said, what's G? It's 2. Take that 2 and find F, and that's how we get the 5. Let's do it again. G of F of 0. So then again, remember it's the inside out. So G of F of 0. F of 0 is 1. We take that and we plug it into the input again, and we find where G is, and it's back at 1. So F of 0 is 1. Plug 1 in for G and get the new output, which again is 1. Another one, F of 1. You're like, what? Just follow the same logic. What is F of 1? F of 1 is 1. So substitute that 1 into F again, and now we get 3. So F of 1 is 1. Then we plug in. Oh, I lied. I'm sorry, y'all. I did F of 0. F of 1 is 3. We take that 3. We go back and find out what F is now. It looks to be 7. So remember, the output of the first one is the input of what you're going to use next. Last example, use a table. F of G of 1. So first off, G of 1. G of 1 is 4. So then we take that 4 and we find F, which is -3. Okay. F of 0. So we find F of 0, which is 1. And we find F of 1 now, which I don't actually see F of 1 on my page, but let's work it out. Sorry, I always do that. I go right, and it's supposed to go down. Let's look at this one. This is going to be G of F of 0. So what is F of 0? It's 1. So now we find G of 1, which is 4. Here we have F of 0. So starting off with F of 0 again, that's 1. So F of 1, we don't see it. It's not in the table. So we say it's undefined. G of 1. So that is, what's G of 1? It's 4. So then we end up with G of 4. It's 8. And that's it, y'all. Okay. Thank you.